Well, good afternoon and welcome to the Iowa Learning Farms weekly webinar series. We're thrilled to have with us Dr. Billy Beck, Assistant Professor and Extension Forestry Specialist with Iowa State University, here today to talk a little bit about some research that he and his team are doing looking at wood chips and water quality. Can select tree species enhance performance of denitrifying wood chip bioreactors? If at any time you have questions for Dr. Beck, feel free to submit them in the chat box to me and we'll get to those following his presentation. So thank you again for attending and I'll turn things over to Dr. Beck.
Thanks, Liz. A big thank you to y'all for sharing your lunch hour with us, and a big thanks to the Iowa Learning Farms for this opportunity to present this kind of cool, smaller project that has led to something a little bit bigger, which I'll share at the end. And just kind of looking at, do different tree species impact the performance of denitrifying wood chip bioreactors? Just a quick acknowledgement of my co-authors. This is kind of a snippet today of this project that we've been going since 2019, and we're getting ready to write it up and submit it to Agrisystems, Geosciences, and Environment. So Alex Boozman, Celia Delury, Dr. Michelle Sapir, and Morgan Davis of the University of Missouri. A special thank you to Celia Delury, who was my 2019 first year honors mentor program student. And she really put all of this into action. So big thank you to Celia there. So today, just going to go over why we're doing this project, some of the background issues we're addressing, and then the objectives of this project, and the larger kind of thing that's led to going on now and into the future. And then one of my big goals today is to get y'all excited about wood, talk about what is wood exactly. And I know you're probably thinking, well, buckle my seatbelt because we're going to talk about wood. But wood is fascinating. It is incredible. I love it. And I really want to get y'all excited about it too. So it's seemingly very boring, but that is not the case. Then a quick overview of some methods, results, and some preliminary conclusions. And then we'll get into kind of the next step, where we take in these results and this effort in the future in this project, what we're calling the Forest to Farm Network. So the big issues we're tackling here, and myself, I've got a forestry and water quality background, so I really like to tackle issues that combine both worlds. So the first one we're looking at is addressing the performance variability and the sourcing issues associated with bioreactor carbon media, specifically wood chips. So if you look around the literature, the performance has been very highly variable with bioreactors around the Midwest. And we kind of, that may be because the sources they're using are of unknown species composition. They just they'll say a hardwood mix or something like that. So the performance out there has been highly variable and probably less than expected. So we want to see if we can select or identify certain tree species or groups of species or characteristics of species that provide an enhanced performance of nitrate removal, but also more of a predictable product. So we get a more predictable bioreactor performance with those. Then also, how do we source this material efficiently and sustainably from our woodlands? So that brings me to the second issue that we're tackling. Me as a forester, I'm very interested in increasing active forest management in our state and across the Midwest. In general, I would say that the biggest threat to Iowa forests is the lack of active forest management around the state. When forests are not managed, they get degraded, they get overrun with invasive species, pests, pathogens, they get removed, they get converted to housing developments, row crop fields, subdivisions, things like that. So when we actively manage our woodlands, great things happen for not only the landowner, but society as whole. So a big part of active forest management is, for example, it's kind of a range of activities, but in a nutshell, what we tend to do is remove certain species, say of poor form, or certain species of less market value, to provide more sunlight resources to desirable species. And when I say desirable species, it's all up to the landowner's goals and objectives. But often, this is Aaron Wright with the Iowa DNR, and the practice he is doing right now is he's marking trees for what's called crop tree release. So he's identified a crop tree, which is a tree that is going to meet the landowner's objectives if kept and provided more sunlight resources. So he's marked these two adjacent trees that are directly competing with the canopy for removal to promote the growth of that crop tree. However, a lot of times those materials and those trees that are removed are either of poor form, smaller diameter, or of species that just have a low market value. So if we can somehow utilize that material in bioreactors, say, we could not only attempt to enhance water quality, but also attempt to encourage active forest management through creation of these new markets. So for this project, this started out very small in the corner of the Water Quality Research Lab in the Ag and Biosystems Engineering Department. Our main objectives were to quantify N, P, and carbon and greenhouse gas production in column bioreactors utilizing wood chips of 4 individual tree species. And then kind of explore the feasibility of how could we do this statewide, sourcing this material sustainably and efficiently from our woodlands to our edge of field areas. Oh boy, here's the most exciting part in my opinion. But no, we're going to talk about where wood comes from first, because I think it's very important to kind of the results that we're going to present here in a second. So very quick crash course on where does wood come from? So trees grow in 2 ways. They elongate from their stem tips and they grow in diameter. So today we're going to be focusing on diameter growth. A lot of things in forestry are based on diameter growth. That's kind of where the money comes from, and it's not all about money. A lot of ecosystem goods and services come from that diameter growth as well. So when you think about this giant red oak here that's no longer with us, it really only has one zone of active diameter growth, and that zone is a few cells thick, and it rings the entire tree, and it's called the cambium. It's a meristem. It's a zone of rapidly dividing cells. So every year, that cambium divides on both sides, creating phloem tissue on the outer edge and xylem tissue on the inner edge. And both those tissues are conductive tissues. So phloem brings the photosynthate, or the sugars, the good stuff, down from the leaves into the rest of the tree. Xylem brings water and dissolved nutrients up from the roots and to the rest of the tree. So always think of the thing, phloem down, xylem up. So the phloem is kind of wedged in between the outer bark and the cambium there. It never really increases in size. It's not really a big component of like a log we would cut down in the woods. So what does increase in size every year through the production of annual growth rings is this conductive tissue called xylem. And xylem is wood. So when we're talking about wood, it is essentially dead xylem that we've harvested and dragged out of our woodlands. So really quick, every year, trees put on in the temperate zone and in general 1 year of xylem. So that's our growth ring that you see and you can count when you chop a tree down. So that ring is often broken up into cells of different characteristics. For example, it often has early wood, obviously put on in the early portions of the growing season, and late wood put on in the later times of the growing season. And you can see in this cross section here, this kind of zoom in cross section here, we've got early wood cells that have, if you notice, those cross-sectional areas are called pores. So the vascular material, it's cut in half and you can see into it, those openings are called pores. So when you hear me talk about pores the rest of the talk, that's what I'm talking about. But check out the pore characteristics between the early wood and the late wood. The early wood pores have a much thinner cell wall and the cells are much bigger in general, where in the late wood, the cells have a much thicker wall and they're much smaller in diameter. The thinking there is in the early part of the growing season, there's ample water and there's not a lot of photosynthate coming down from the leaves because there's really not many leaves yet. And the leaves that are coming out are going into stem elongation and not diameter growth. In the later part of the year with lower water and now abundant photosynthate from the leaves that have been out for months, they've had more photosynthate or sugars to put into cell wall thickness. So we get some really nice thick cell walls in the late wood portion of the growth ring. So a lot of times if you look at wood like this red oak cross section on the left, you see those early wood pores, which are very large, and then the late wood pores, which are very small. And that's just for a select group of species. It's all arranged very differently, and we'll get into that in a second. So every year we get a new ring of xylem, which is wood. So across the board, wood in general all species is about 50% carbon. That's just all species across the board. So that's kind of cool. So in a sense, wood is very similar across tree species. Additionally, its specific gravity, or in this case, we're using it kind of as a proxy for density. If you bust it up and pulverize it, so eliminate all the pore space, just the actual wood material, so cellulose, hemicellulose, and lignin, is about 1.5, again, across the board. So wood is very similar across species, wood itself. So why in the heck would a black walnut log weigh so much more than a cottonwood log of the same dimensions? What really all comes down to macro and micro porosity. So kind of the arrangement of that wood in the whole matrix. So wood is kind of the same across species. How it's arranged, the porosity differs, and that drives all kinds of things from strength, rot resistance, end usage. It makes the amazing array of wood characteristics that we see in our Iowa woodlands. So macro porosity kind of talks about the arrangement of the vessels within the annual tree ring. So this is what's called a ring porous pore distribution. It's a way to identify wood. Just like identify trees, you look for certain characteristics in the wood. So ring porous has very, very large vessels in the early wood, and they shrink and the cell walls get very, very thick in the late wood portions. So that's ring porous species. Most of the species in Iowa, I shouldn't say most, 60% or so, are what's called diffuse porous. So there's not a great difference in vessel size or cell wall thickness between the early wood and the late wood. And it's kind of hard to see the rings, where each ring starts and stops. So that's kind of the first thing I look at wood ID is it ring porous or is it diffuse porous? So if you look back, I'll go back a bit here. In the middle of each one of these cells is called the lumen. And the size of that lumen and the thickness of the cell wall really determine the porosity of that wood. Another cool way that wood is similar but very, very different, each species has this diverse assemblage of chemicals, tannins, fats, resins, oils, that are kind of collectively known as extractives. And these give each wood species its unique color, odor, rot resistance, medicinal properties, really, really cool stuff. And this is kind of some of the species we looked at just soaked in water for 24 hours. So these are kind of the water extractable extractives that you would see. So each species has a very distinct signature, a chemical signature, which drives a lot of its uses and a lot of its beauty as well. For example, extractives give black walnut its coveted, globally coveted heartwood color, that deep chocolate brown that is makes it Iowa's most valuable timber species by far. So it's all about the extractives. So we didn't look at that in this study, but that could be a future potential research area, is how extractives influence the microbial community in these denitrifying bioreactors. All right. Real quick overview of the methods, coming from harvest all the way into the lab. We started out just looking at 4 species. This was a freshman honors project, so we didn't want to get too wild. But our first hypothesis was, let's check out a gradient of densities. So we wanted to go from very, very low density to very, very high density. And we also wanted to select species that are often removed and killed and underutilized in forest management activities. So these are the 4 that we came up with our gradient here. We have eastern cottonwood, which is very low density. Again, thin cell walls, bigger lumens. Hackberry, which is the next step up in density. Hard maple, which is a catch-all for red, sugar, and black maple. And shagbark hickory, which was our most dense species. So we harvested these in central Iowa in February 2020. We took the trunk portion only, which was important because if you use the tops and a lot of twigs, you get a lot higher bark to wood ratio, and you get some kind of trash and debris in there as well. And they were around 6 inches in diameter. So some smaller, what you would typically remove during forest management activities. And then we cut them, chipped them up using our tractor mounted PTO chipper. Not too uncommon for landowners to have one of these tractor mounted wood chippers there. So those were our 4 species of interest. Then in the lab, we constructed these upflow column denitrifying bioreactors. And we looked at kind of a standard flow for the first 150 days. So we flushed these nonstop flow with nitrate and phosphorus spiked water. We did an initial 150-day sampling period, residence time of about 9 hours. This was followed by a 105-day period of wet dry cycling to better mimic kind of in-field conditions. And then we did a lot of analysis on the wood chips themselves. I'm not going to get into too much today, but that's often not heavily reported in the literature. So like, how is it chipped up? What was the chip particle size? Things like that. So we did a lot of characterization of the wood chips themselves. We only had 1 rep per treatment. Again, it was a freshman honors project. We had limited room. And today I'm really going to hit on nitrate, dissolved reactive phosphorus, carbon, and greenhouse gases, methane and nitrous oxide. And then I'm really going to focus on the initial 150-day sampling period, just for time. We're not going to get into the wet dry cycling. So I wanted to start off with this. This is just a cool image that goes back to species density and just the differences we see in using individual species as wood chips. So again, we've got our gradient here from left to right, cottonwood being the least dense, shagbark being the most dense. And when we ran these through the chipper, they chipped up very differently. So cottonwood, again, very low density. It had a nice, even particle size spread, very consistent size in the chips that were produced coming out of the chipper. As you go up and up and up, hackberry, hard maple, you get to the end of shagbark. Shagbark was so dense, it essentially shattered into large chunks when coming out of the chipper. So if you want to make a consistent size with these species, you really have to manipulate the speed at which you feed this wood into the chipper to get a consistent chip size. But I thought this was a really cool visual. We quantified this as well in several different ways, but this is a neat visual to show that wood is different. It chips up very, very differently, different species. So something to think about, especially with hydraulic retention time in the bioreactors. All right, so getting into our results, again, the first 150 days, this is mass removal efficiency. So 100% nitrate goes in, what percent was removed and came, and then thus measuring the effluent of these bioreactors. So as you can see over time, performance kind of went down, 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 which is expected. But the 2 leaders, as far as percent N, and for this, we're assuming nitrate is the dominant form here. The 2 leaders were hackberry and shagbark hickory over the 150 days, removing about 62% for hackberry and about 57% for shagbark hickory. Hard maple and cottonwood were the 2 lowest performers as far as N removal, with 36 and about 23% total removed from the input into the effluent, with our influent concentration being about 30 parts per million. So hackberry and shagbark were the top performers in that initial period for the first 150 days. So mass removal, so not percent, but actual mass removal, cumulative, kind of same story. So this is a rate, or cumulative, grams of N per meter cubed of chip. So over the 150-day period, again, hackberry and shagbark hickory were the 2 leaders in performance, with hard maple and cottonwood lagging behind. And the mean daily rate over the 150 days of grams per N removed per cubic meter per day, hackberry was around 21, shagbark hickory around 19, and then about 13 and 9 for hard maple and cottonwood, respectively. So again, nitrate removal mass, hackberry and shagbark hickory were the top 2 performers. So phosphorus, we also looked at phosphorus, dissolved reactive phosphorus mass removal. So cumulative here, just like the previous slide. So grams of P per cubic meter of chip. Again, shagbark hickory and hackberry were the 2 leaders over the 150-day period, with cottonwood and hard maple trailing behind. So shagbark hickory about 0.21 grams of P per cubic meter per day, hackberry about 0.18, and then cottonwood and hard maple fairly behind there as mean daily rate removals. So the story is kind of becoming, there's a story here developing. And then for mass removal, again, same story. Shagbark hickory removed about 35% of incoming P, dissolved P. Hackberry removed about 30% of incoming dissolved P. So the point here is just there's a difference coming together. There's a difference becoming more visual here, that certain species are having different performances versus others. Carbon, so shagbark hickory again and hackberry once more had the highest mass in the effluent from the bioreactors. So most carbon mass exiting the bioreactors, a mean daily rate of about 8.5 for shagbark hickory and about 7.6 for hackberry. Hard maple not too far behind, and cottonwood very low at about 2.8 grams of carbon per meter cubed per day. So we also want to look at pollutant swapping. So is there a trade-off? Are we trading, as my colleague Dr. Morgan Davis says, are we trading a water quality problem for an air quality problem? So not to get into the whole like reduction ladder here, but we looked at methane production and nitrous oxide production dissolved in the effluent of these bioreactors. So for methane, at about 120 days, the shagbark hickory really started to take off in methane production. So the thinking behind this is perhaps the shagbark hickory bioreactor became much, much more anoxic than the remaining three species, but they took the lead there. The shagbark hickory kicked out the most cumulative mass of methane from its bioreactor compared to the other three species. And honestly, the mean rate was the only one that was in the positive as far as milligrams per cubic meter per day. So shagbark hickory top on methane production. Nitrous oxide. So are we having complete denitrification? If not, most likely we're going to have a higher N2O production from these bioreactors. So the top two, we kind of flipped it here now. So before hackberry and shagbark were kind of dominating things. Now for N2O production, we're seeing cottonwood and hard maple taking the lead on cumulative mass of N2O produced with daily rates of 0.64 and 0.57 grams per cubic meter per day from cottonwood and hard maple. So if you look at all these trends, our density hypothesis didn't really hold true. We kind of thought, okay, maybe the most dense species has the most labile carbon and thus will have the highest denitrification and whatnot. Well, that's true, but the bookends, shagbark, hickory, and cottonwood, but hard maple and hackberry are kind of flipped. So hard maple, much more dense than hackberry. It flipped in the results. So maybe density is not the whole story there, as our initial hypothesis was. So preliminary conclusions after 150 days, just kind of, again, a snippet of the results here for time today. Shagbark, hickory, and hackberry had the greatest N and P removal rates and efficiencies. They also had the greatest carbon effluent masses, and they also had the lowest nitrous oxide production rate. So perhaps more complete denitrification going on with those two species. Shagbark hickory, though, did produce the greatest mass of methane dissolved exiting its bioreactor. So going back to our little woods science lesson there, we were trying to think of, okay, what the heck do hackberry and shagbark hickory have in common besides they're often removed and they're kind of a higher density species? So kind of the one thing we notice first off is they're both ring porous vessel distribution species. Cottonwood and hard maple are diffuse porous. So again, thinner cell walls, larger lumen, higher overall porosity. So again, annual growth rings are comprised of early wood. In this case, there's a distinct, the early wood pores are distinctly larger than the latewood pores in ring porous species here. And this is a cross section of hackberry, and you can see the beautiful wavy pattern of its latewood pores. It's in the elm family. So hackberry has this beautiful, distinct, wavy latewood pore pattern here. So again, ring porous, we've got large early wood vessels, smaller, thicker walled latewood vessels as we go into the growing season. And then cottonwood hard maple, again, we're diffuse porous. So this is a hard maple cross section. Big thanks, a lot of these big thanks to Dr. Doug Stokey, emeritus professor at Iowa State here. Many of the slides and consultations were credit to him. So diffuse porous species, you have a hard time kind of detecting the rings. You can see them here, but they're not as striking as the ring porous species are. So that was the first big thing. And we're going to have to do more lab tests on this. I would love to dig into diffuse versus ring porous and other things like extractives and how those influence bioreactor performance. But this is the biggest thing that really popped out as why was the pattern that we were seeing, maybe occurring. So kind of blowing this up to the statewide level, the first thing I thought when we started getting these results was like, well, geez, if you look at the LIT and like the Iowa Nutrient Reduction Strategy and all those, it's about 200,000 bioreactors needed in Iowa alone to meet the reduction laid out in the Iowa Nutrient Reduction Strategy. So that's a lot of bioreactors. So if you average 100 cubic meters per bioreactor, it's a lot of wood chips. That's 20 million cubic meters of wood chips. I was starting to think, do we even have that many trees in the state of Iowa, let alone these species and of those smaller diameter classes? And the answer was yes, I believe we do. The first thing we did is we did a chipper test. So we took logs of known dimensions and known volumes, ran them through a chipper, and then we recorded the volume of chips that each produced. So with that, we determined that we were going to need about 14.3 million trees to satisfy these 200,000 bioreactors. So does Iowa have 14.3 million trees of these species and sizes? So I looked into the giant spreadsheets of the USDA Forest Inventory and Analysis Program. This is basically an inventory keeping tabs on our forest growth and composition every year across all 50 states. I looked them up for Iowa. And yes, we do. We do have this volume of these species and sizes out there in our Iowa woodlands. And this was a back of the envelope calculation, but it was encouraging. And talking to foresters and just being out in the woodlands, I think this is true. Speaking of foresters, they also say yes. We were talking about, okay, if we need this much volume for a bioreactor of these species, given growth rates and given a typical Iowa setting, can producers almost grow their own bioreactor perpetually and refill these chips, every X years as needed? So just really, and again, each site is different, every species is different, but back of the envelope calculations, yeah, we believe a landowner may grow volume for a 100 cubic meter bioreactor on about 3 years, so not much land, over 3 acres over 15 years. So again, potential there to perhaps grow your own bioreactor. So this is the next step. Like, how do we do this? How do we source this material effectively, efficiently, sustainably from our woodlands to the edge of field areas and perhaps enhance performance and also encourage active forest management? So we received funding from two sources to do two facets of this new project here. We got funding from the U.S. Forest Service and funding from NRCS over the next 5 years, 2022 to 2027, and what we're calling the Forest to Farm Network. So this is really essentially trying to connect the loggers, the timber buyers, the foresters, the agricultural producers, the water quality practitioners into a large online and physical network to get this material removed from the woodlands sustainably and into the hands of the water quality practitioners and ag producers, so they can source this material when needed and have hopefully a consistent performing product. So again, trying to work on water quality and forest stewardship at the same time. So this is going to be a pretty extensive online directory. So for example, water quality practitioners could input their information, like these are the projects we've got, these are the volumes we need, these are the delivery dates, this is the storage capacity, all that kind of great stuff. The loggers, the timber buyers, the foresters could look up and say, okay, we can source it from here, this county, we can deliver it to you in that time frame. So connecting all those folks to get this stuff rolling. But to back up what we're kind of saying, we need to know if these things are going to actually work at the field scale. So we have an incredible opportunity to install 20 field scale bioreactors using individual tree species. So these will be going in this fall, spring, and then throughout 2023. So we selected hackberry, hickory, green ash, which we didn't test in the lab, but we know it's going to have an abundant supply over the next 15 years or so. And we didn't talk about this today. We're also looking at shredded material. And then, of course, the control, which is the standard hardwood bioreactor mix that they're commonly used in bioreactors across the Midwest. So that'll be neat. We'll be installing them and monitoring them just to get more buy-in, like, hey, these things are working and these things do work. And thus, hey, maybe I should think about sustainably managing my woodlands on my farm. And this could be one source of additional income and benefit to the overall farm enterprise. And of course, me being an extension person, I wrote in a ton of water quality and forestry, often duly occurring extension efforts. So products, videos, field days to get all that crew together, connecting the loggers, the timber buyers, the foresters, the ag producers, and the water quality practitioners to get this forest to farm network off and running. So with that, the statement of the day is wood is good. I hope I got you excited about the often thought of as boring concept of or subject of wood, but ton of people to thank here. The ABE Water Quality Research Lab, there's too many folks to list there, but y'all know who you are. Huge thanks. The First Year Honors Mentor Program and all these great folks right there, especially Dr. Doug Stokey, who's kind of my wood mentor here at Iowa State. So please hit me up anytime to talk trees and water quality, and you can follow my antics on the socials there. But I guess with that, Liz, I think we'll open it up after we have these announcements for some questions.
Yeah, thanks, Billy. So if you watched today's webinar, feel free to get a CCA credit. Feel free to send me an email today by 5 p.m. My email is there on the screen, and we'll leave this up as we work through questions. So feel free to send me that email with your CCA number and your name so I can get your credits submitted. We've had a couple questions come in, but feel free to continue submitting those as they come up. So maybe you'll want to swing back to this one, but in the second graph of results, what explains the lag in the shagbark hickory? That's the first part of the question.
Yeah, was it this one, correct?
Yes.
Yeah, so I think our thoughts on that, and we also did, I didn't present it here today, but we did what's called a batch test, which is a fairly simple test where we only did 9 hours of retention time in like mason jars sealed up. And in that test, we also used a species of even higher density. And I think there was just a lag time of breaking down that carbon because it's incredibly dense wood species. So I think it just took a little bit of time to either the water penetrate it or the microbes to get after that carbon. I don't know. We definitely noticed that lag in the shagbark hickory. And almost like the more dense species took longer to warm up, but then they eventually took over in the lead. So great question, but that's something we're gonna have to look into in the future. But something with the density, I think, might have played a role with that.
And can you also maybe recap or summarize why the chip size is significant for the filtration?
Oh yeah. So it's kind of all about hydraulic conductivity, right? So if you have a tube of sand and you have a tube of gravel, which tube would the water flow faster through? Well, probably not probably. It would flow faster through the gravel because there's higher porosity in between the particles than in the sand. So if you have these large shagbark chips versus the smaller cottonwood chips, you would have to adjust your flow rate to get the same residence time between the two species. That's why it's very important to kind of know that you're going to have to control how you feed the chipper with these to produce a consistent size between species.
So length of the pit and or treated area would be longer if you use the less efficient chips. So that they're questioning, would you need to make your bioreactor longer if you're using some of these less efficient chips so that they're interacting longer?
Let me think. So with longer, yeah, you see that's almost comes down to a design question too, because the size of the bioreactor is based on the amount of drainage area and flow that you're getting delivered to it. So if you make the bioreactor larger and you don't have the flow to satisfy that, there's going to be problems like methyl mercury and things like that, I believe. So I would say yes, in general, yeah, you would need more material to get the same performance as a smaller material, the more effective species. But I think you got to watch your design size because it's really dependent on the size of the drainage area and the flow being delivered.
And it also drive up costs then too if you're having to use that much more chips.
Right. And ideally, I mean, in the future, it'd be neat to see like, okay, is there a recipe? Like, all right, we want to throw in 20% cottonwood because it has an incredible performance right out of the gate for the first year. But then we know shagbark, hickory will have the long-term kind of consistent effect there. And two, in the field, you know, these things aren't saturated the whole time. They go saturated, unsaturated, saturated, unsaturated, which leads to wood decay. Inundated wood, saturated wood has a very slow decay rate. Exposed wood has a quick, faster decay rate. And these species have a much very different rot resistance. Again, going back to those extractives and their densities and things. So shagbark, if it's performing high, and we know that it's more rot resistant than cottonwood, maybe that's a factor that goes in there as well. It could be longer lived.
And you kind of noted this, that there was a question earlier on about ongoing experiment. The next stage is looking at these outside of the lab over these 20 that you're going to install. So you will be looking at additional years of results, but at a real scale level.
Correct. Yep. So if we're going to do this push to kind of encourage sustainable forest management, we figure we better get some field numbers to back up what we're doing or what we're promoting. So
someone was curious, how long should one wait between the chipping and the installation of the bioreactor? Is there any dry down time needed for these chips?
I don't think there's a dry down time. I think if you look at the NRCS specs, and I'm going to get a ballpark here, I'm not going to nail it right on the head, but I think it's about 120 days. They don't want the chips lying around for more than 120 days prior to going into the reactor. So practically, you want to chip these up very soon after harvest because as wood dries, it's very hard on the equipment to chip up. So if you can chip these up as fairly soon when they still have a lot of free water in them, that will really be easier on the equipment than waiting for these to dry a couple of years and then trying to grind them up then. But I think NRCS says it's about 120 days, and I think there's research to substantiate that. Don't quote me on that, but the spec is 120 days.
So asking kind of what your prediction might be, knowing what you know about green ash and its comparability to the other species you've tested, where do you think it falls potentially between these four species?
I think it's going to be somewhere in the middle. And I can't believe I'm doing this. I'm drawing a blank. Let me look up what its pore arrangement is. It's like riding a bike, it'll come back to me here. So, all right. If it's, our predictions from this based on the vessel arrangement, if it is ring porous, I think it's going to lead more towards the shagbark hackberry. Let me see. I taught this class 2 years ago. This is embarrassing. So, right. All right. It's ring porous. So I would say it's more of the hackberry. I'm going to predict a higher performance from hackberry and shagbark. It's similar to hackberry and shagbark. So
So curiosity, if there is any work being done to evaluate the sizing of the wood chips. Now you kind of tried to make them similar here, but any look into that?
Not the chips. What is part of this next step is we're looking at shredded material. So after the derecho, I'm sure if you ever drove through Cedar Rapids, you saw the mountains of shredded material that's generated from what's called a tub grinder, which is a different chipping mechanism than a traditional tree chipper. It basically just pulverizes the wood. You can put root balls, you can put all kinds of stuff in there, and it just grinds it right up. So it makes these long, kind of linear shredded particles in there, which are not currently, spec'd out with NRCS because of potential issues with hydraulic conductivity. So we're not looking so much at chip size. That's a really interesting point, though, and something that we should consider. But we are looking at this shredded material and how that would perform, because there's often in urban areas an ample supply of that tub grinder derived material. The only thing I can think of as far as chip size is, again, it impacts hydraulic conductivity, but also something to think about is rot resistance and surface area. So obviously cottonwood, it's like clay and soil, smaller particles, higher surface area. Larger particles, lower surface area to volume ratio, potentially a higher rot resistance. So yeah, I definitely think size is a factor, but we're not looking at that. I think it's a good idea. We should consider it, but initial plans, we're not looking at size.
So probably while you've got that book out there, someone's curious on an evergreen side of things, if pine would perform like a cottonwood rather than the more dense trees.
So conifers are actually quite dense as well. The term hardwood, softwood is kind of misleading. There's a lot of hardwood species that are less dense than, say, southern yellow pine that you would find at Menards or Lowe's or something. So pines, I don't know. We just don't have the pine supply here in the state of Iowa. We only have, a few handful of native conifers in general, and only one pine species, and that's in pockets along the Mississippi River in the Northeast. So I would predict a lower performance from pine. So.
And this kind of goes back to the results graphs you were showing. They noted that the drop in nitrogen removal after 120 days looks a little bit discouraging. Is this related to the size of the experiment, and what could you potentially expect on a field scale?
So I would probably defer to my expert colleagues on this, but if you look, I think in the lit, even in the field, it tends to taper off over time. You get this huge, I think what happens is the label carbon gets used up rapidly for denitrification, and then it kind of starts to drop and level off. So I'm predicting kind of a similar spike here. You see a big carbon flush and spike in removal efficiency in the start, and then it kind of tends to level off. And if you look around the lit, I mean, it's coming back down to like the numbers you'd see reported. So I'd predict the similar pattern. It's gonna be It's gonna be exciting to see what happens over the years with this project. So
would you happen to know the standard tree wood that's being used for bioreactors now, like what the makeup of that is?
Yeah, that's a good question. I actually have some dried out in the lab up there. I think they just call it a hardwood mix. So poking through it, it's a mix of like black walnut, probably ash, elm. That's a good question. I should get up there and ID it. But it's basically what you see is it's labeled as like conventional hardwood mix.
This is our last question here. What's the latest understanding on methyl mercury production from bioreactors? Ooh. And maybe this is one to be a whole nother topic. And are there design considerations to help minimize that production?
I will defer most of that. My novice design knowledge, and I'm not an engineer by any means, is that you really need to match up the flow rate with the size of the bioreactor to make sure you get ample or appropriate flow, so you don't get extended periods of drawdown to reduce methyl mercury. So I would defer that to some of my colleagues on this, my co-authors. So
yeah, and actually the date hasn't quite been set yet, but yet this year we're going to be doing a virtual field day. with folks from ABE looking at their pumped bioreactor, where they're trying to reduce the times where there was that drawdown to minimize the methyl mercury production. So it's next to a creek, and they're trying to pump in some of the water from the creek to help maintain flow through the bioreactor. So I know there's some folks working on that, still kind of in that pilot scale. So stay tuned. Keep your email on alert for that virtual field day announcement yet this year, looking at that pumped bioreactor design. So if you want to go to that last slide one more time, we hope that you all can join us next week as we hear from Emily Waring, a former PhD student here in the Department of Agricultural and Biosystems Engineering, talking about some research being done at the Sutherland of the Northwest Research Farm, looking at the influence of fertilizer timing on nitrate loss and crop yield. So we hope you can join us next Wednesday at noon, and thank you for tuning in today. Take care and have a great week ahead.
Thank you all. Thanks, Liz.